Welcome to this video on material and binder jetting, a comprehensive technical analysis of advanced droplet-based additive manufacturing processes. In this video, we will explore the physics, chemistry, and process control governing high-precision additive manufacturing. Droplet additive manufacturing generally encompasses two main processes: material jetting, which deposits photopolymer droplets that are cured via UV light, and binder jetting, which uses a liquid binder to join powder particles, requiring subsequent post-processing. These technologies have evolved significantly since the development of 3DP at MIT in 1993, and today they enable submicron droplet control and complex multi-phase fluid dynamics. The core operating principles for these systems involve three stages: atomization to generate precise microdroplets, spatial deposition onto the build platform, and final consolidation through either UV curing or powder agglomeration. Next, let's examine the fundamentals, rheology, and process control specific to material jetting. In drop-on-demand systems, piezoelectric actuators create acoustic pressure waves within the fluid chamber to overcome surface tension at the nozzle, enabling the ejection of discrete, satellite-free droplets. Droplet formation is governed by the Z number, which is the inverse of the Ohnesorge number, relating inertial and surface tension forces to viscous forces. A stable printing range is typically between 1 and 14. As noted in the literature, stable drop generation is bound by fluid mechanics, where the lower limit is determined by viscous forces preventing ejection, and the upper limit marks the onset of satellite drops. Ink formulation must balance viscosity and surface tension. Viscosity must be low enough for micronozzle flow, often achieved by heating, while surface tension must be high enough to prevent nozzle dripping, but low enough to ensure proper substrate spreading. We now examine the photopolymerization mechanisms in material jetting, focusing on resin chemistry and UV curing. In situ UV curing involves an ultraviolet light source attached to the print carriage, which exposes deposited droplets to radiation, triggering photoinitiators and initiating rapid cross-linking into a solid polymer network. Different polymerization mechanisms offer distinct properties. For example, free radical polymerization is extremely fast, but susceptible to oxygen inhibition, whereas cationic polymerization is slower but immune to such inhibition. Critical process control variables include jetting frequency, which impacts carriage speed, droplet spreading governed by the Weber number, and thermal tuning to keep fluid viscosity within the optimal printable window. Finally, a heated planarization roller is used to level the resin to a precise height post-deposition, ensuring dimensional tolerance and uniformity throughout the build. Material jetting enables multi-material blending. By jetting droplets of rigid and elastomeric resins in specific ratios, we can engineer parts with varying macroscopic properties in a single print. Support structures are necessary in material jetting, as droplets require a substrate. We utilize wax-based, soluble, or optimized interface layers to enable complex geometries and facilitate easy post-process removal. Moving to binder jetting, this process relies on different physics, specifically powder bed dynamics and capillary action, to build parts from metal, ceramic, or sand powders. In binder jetting, the printhead deposits a liquid binder onto a dry powder bed. The material's particle size distribution and morphology are critical for flowability and achieving maximum packing density. Key powder characteristics include packing density, which optimizes void filling, avalanche angle, which measures flowability, and particle size, which balances resolution and sinterability against forces like van der Waals. Droplet powder interaction is a dynamic process. Impact energy can cause cratering, while capillary forces dictate how the binder penetrates into the interstitial voids of the powder. Successful bonding depends on mastering binder chemistry and controlling saturation dynamics, which govern the final mechanical integrity of the printed part. Binder systems vary depending on the material, but they must all interact predictably with the powder bed to ensure uniform consolidation during the build. Binder saturation, or the percentage of void space filled, is a critical process variable. Optimal saturation balances the need for green strength against the risk of dimensional distortion. Drying kinetics must be carefully controlled. In-process drying prevents feature smearing, while preventing excessive drying avoids binder migration, which can lead to anisotropic shrinkage. Binder jetting requires significant post-processing to transform the fragile green part into a fully dense final component. The green part is held together only by binder bridges between particles. Since green density is typically around 50 to 60%, handling at this stage requires great care. Post-processing starts with bulk curing to maximize strength, followed by depowdering, where excess material is removed and recycled for future print jobs. Thermal debinding is the next critical step. We must carefully pyrolyze the binder to prevent carbon contamination, resulting in a fragile brown part ready for sintering. Finally, the sintering stage densifies the part through atomic diffusion or liquid phase mechanisms, completing the journey from loose powder to a solid functional component. Alternatively, infiltration offers a method for near net shape accuracy. Instead of sintering to full density, the porous brown part is infiltrated with a lower melting point alloy, such as bronze, into a stainless steel matrix. Standard sintering often leaves residual porosity that can reduce fatigue life. Hot isostatic pressing, or HIP, addresses this by applying high temperature and gas pressure, closing internal voids to achieve theoretical density. This densification profile illustrates the process, starting from approximately 55% density and progressing through debinding and diffusion, reaching over 99% density post-heat. Let's perform an analytical comparison between material jetting and binder jetting to understand their distinct process characteristics. When evaluating capabilities, both methods differ significantly in material requirements, resolution, and post-processing needs for final part completion. In material jetting, common defects include satellite droplets that degrade surface finish, nozzle clogging from particulate accumulation, and delamination due to insufficient curing between layers. Conversely, binder jetting challenges include ballistic ejection of powder, anisotropic shrinkage during sintering, and potential carbon contamination from incomplete binder removal. A convergence of these technologies is emerging in nanoparticle jetting, which suspends metal nanoparticles in a jettable carrier to combine material jetting resolution with metallic output. Resolution limits in these processes are fundamental. Material jetting is constrained by nozzle diameter, whereas binder jetting is limited by particle size and capillary spreading within the powder bed. Environmental considerations are also distinct. Material jetting requires managing hazardous resins and ozone, while binder jetting necessitates safety protocols for handling fine metal powders. To optimize these processes, computational modeling is essential for predicting the physics of droplet formation and material behavior. Simulation approaches include VOF for fluid dynamics, DEM for powder bed interactions, and for predicting sintering-induced deformation and stress. Since sintering causes significant shrinkage, algorithms use compensation matrices to distort the initial digital model, ensuring the final part meets design specifications. Finally, we must consider the industrial economics and the scale of production for these two additive manufacturing technologies. While material jetting is ideal for high-fidelity prototyping, binder jetting enables massive volumetric throughput, making it highly effective for batch mass production of complex metal parts.